Welcome back, guys. In this video what I want to do is discuss a simple application of matrices and show how they can be useful in solving problems. Now, you've probably all seen this application before, but I'm going to go through it again anyway because I want you guys to know that matrices are really not that scary. A lot of people get freaked out when they see matrices or they hear linear algebra, and really it's just a convenient mathematical shorthand for actually many different sorts of symbols and provides a general framework. So with that, we'll start out with the basics of matrices. Now, one application of matrices is in solving what we would call systems of linear equations. Now, you guys have probably done this before, probably in junior high and even high school, but it'll seem like I'm belaboring this point, but I'll really show this first in terms of how the equations are solved and then how a matrix representation can help out with solving this. So let's say I start out with a simple system of equations. Say x plus 2y equals 3 and 4x plus 5y equals 6. Now, you guys have all solved these before, and there are standard steps such as elimination, substitution, those sorts of things. So what I would do if I was looking at this is I'd say, hey, you know what? We have an x in the first equation. I kind of want to call this equation E1 and then this one E2. That's an E, sorry. And so what I'll do is I'll notice, hey, you know what? I can get rid of x in the second equation by subtracting 4 times the first equation from the second equation. And if I do that, so I'll write E2 minus 4 times E1 is E2. I'm replacing the second equation with itself minus 4 times E1 to get rid of x. So x goes away in the second equation, and then we have 5 minus 4 times 2, which is 5 minus 8. We're left with 3, negative 3. And then we have 6 minus 4 times 3, which is minus 6. So with that, we have this set of equations. And from here, probably the best thing to do would be to divide the second equation by minus 3. Alternatively, I'm going to write it as multiplying it by negative 1/3. And the reason for that is generally division can be regarded as multiplication in these sorts of settings, and it's easier to just have one operation. From there, I can rewrite this set of equations as x plus 2y equals 3 and y equals 2. And from this, we've now solved for y. So we could substitute y back in to the first equation, which would be in terminology called back substitution. But what I'm going to do is I'm actually going to keep going. I'm going to say, hey, you know what? Now that we have y isolated, let's subtract twice the second equation from the first equation. So that would be E1 is now E1 minus twice E2. And that'll leave us with x plus 0y equals minus 1, and then y equals 2, because I'm taking 3 minus 2 times 2, which is minus 1. And now from here, we've pretty much solved for both x and y, so I can rewrite x equals minus 1 and y equals 2. Pretty standard stuff. You guys have solved these before. Linear algebra provides a framework for explaining the set of solutions to these sorts of equations in higher dimensions. So obviously you would think about these as two lines that intersect at a single point, and that point being at minus 1, 2. But in higher dimensions, it's hard to have that sort of intuition. But we can still solve it and still have a pretty good sort of foundational intuition by generalizing this sort of dimension. So to show how this relates to matrices is what I'm going to do is I'm going to kind of work backwards. And all I'm going to do is just write this in kind of a different way. So I'm just going to put brackets around this the second to the last equation above x equals minus 1 and y equals 2, and get rid of the equal signs and replace them with a line. And that's just, I'm drawing the line there just so I separate the right-hand side from the left-hand side, because otherwise it could get confusing. Now what I can do is I can just get rid of the x's and y's and just keep them as numbers, and get rid of the plus and minus signs too, because we don't want to have to write that every time. We know if we keep our spaces consistent where each of these variables are going to lie. So what I'm going to do is I'm just going to put a 1 in front of the y and a 0 in front of the x position in the second equation, and then just get rid of the variables altogether. So that'll leave us with this. Now working backwards, we can go to this last equation on the bottom left, and we can do the same thing. We can replace y with 1, and then that x, which isn't there, with a 0. And but first, of course, we'll draw the brackets and get rid of the equal signs, draw a line. Then we'll go ahead and get rid of the other stuff. Moving up, we'll go ahead and add the brackets, get rid of the equal signs, and get rid of the x and y as well. And finally, in this last equation that we started with, I can go ahead and write the brackets, draw a line, and get rid of the variables. And this is actually a process called Gaussian elimination, and it's useful for solving linear equations like this, systems of linear equations, and describing their solution sets. But actually, Gaussian elimination has a lot more applications, which we'll be getting into later also. So if you're trying to solve these equations, this is a great place to start. You can just write the matrix, draw a line, and add the right-hand side with the what the equations are equal to, and then just go ahead and perform these steps so that you have this sort of structure of ones along the diagonal, which basically tells you the first variable in that position that you would assign there is -1, the second position is 2. And the reason it's helpful to think about this is any sort of operation you could do to these sorts of equations, you can also do to for instance, a matrix. For instance, if I wanted to swap the positions of these two, that's like just swapping x and y in like how they're ordered, which one's on top and which one's on the bottom. And you can totally do that. Like I could totally come over here and write this as 4, 5, and then a 6, and then 1, 2, and then a 3. So really any sort of operation you can think about doing with systems of equations, you can do to matrices. And especially with doing this sort of row reduction, it's a really cool process. So I hope you guys got a lot out of this. You've probably seen this before, but you'll see applications of this, and I wanted to make sure that I drew the bridge between the systems of linear equations and matrix notation, because it's really not all that different to what you guys are used to seeing. All right, see you guys in the next video.